This one goes out to Celeste, who had such nice things to say about the flipped classroom. So anyways, let's go ahead and get started. We're going to be talking about forces in 2 dimensions, and so that's going to require some vector addition and vector resolution. We want to look at how we can do the vectors graphically. We're also going to look at adding the vectors algebraically. So it's going to be a little bit of a Algebra 1, Algebra 2 review. Vectors, remember, have magnitude and direction, so we need to figure out both what the magnitude is, which is going to be probably the easier part, and also the direction that they're pointing in. So up until now, all of our vectors have been along one dimension, so they've either both pointed in the same direction or they pointed in opposite directions. We used a technique where we basically put the tail of one vector to the tip of the other vector, and we just saw how long they were. It's not going to work though when they don't point in a straight line. There are some things that we can do though. As long as we have a vector, as long as we keep the vector pointing in the same direction and we don't change its magnitude, even if we move the vector around on the page, the vector doesn't change. So if we have two vectors like A and B and we want to add them up, we could simply line them up so that we put down A, and then we put the tip of B up to the head of B, and then draw a line from the very beginning of A to the very end of B, and that new resultant vector is the vector that we're interested in. You can see if it's a nice right angle, you might think of Pythagorean theorem. As a matter of fact, that's one of the ways that we go ahead and do that. So we have our two vectors here, and then we add the last one in, giving us the resultant. You can move the vectors around as long as you don't change the direction or the length. You haven't changed the vector. They're still the same vector. So if we have this, we do want to do a vector. You might recognize this as Pythagorean theorem. Hypotenuse squared is equal to the sum of the squares of the other two sides, which is essentially what we have here. If vector A is at a right angle to B, then it's simple. What happens if the vectors are not at right angles? We could use law of sines. Law of sines basically says that there's a consistent ratio. If you take the length of the hypotenuse and put it over the angle, it's not really a hypotenuse because we don't have a right angle, but if you take the longest side and put it over the sine of the longest angle, it's going to equal the same as the length of A, and over the sine of its opposite angle, or B over the sine of its opposite angle. Works out that way. It's pretty easy. We also have the law of cosines, which looks almost like Pythagorean theorem, except we add something to the end of it. This negative 2b AB cosine theta. So this just kind of describes it. You could stop it and read the video if you want. So let's say we want to find the angle of two displacement vectors. We have 15-kilometer displacement and a 25-kilometer displacement. We're going to first of all set them at 90 degrees to each other, making it easy. We'll use Pythagorean theorem. Then we have a 135-degree angle, so we're going to have to use something other than Pythagorean theorem to solve that. We're going to start by sketching the two angles, filling in the resultant. And again, we're going to first of all solve this with a 90-degree angle. If we're solving it with a 90-degree angle, Pythagorean theorem. So we put 25 and 15, and square root of 25 squared plus 15 squared is 29. You might want to try that. Stop the video and try that if you want. Gets a little bit more complicated when we have something other than a 90-degree angle. We're going to have the 135-degree angle, so we're going to use the law of cosines here. Once again, we're going to fill in for A, 25 kilometers, B is 15 kilometers. Remember, this is A and B here again, so 25 and 15, and finally we have the cosine of 35. Once again, you might want to try this on your calculator just to make sure that you get 37. If you're not getting 37, come on in. We'll talk about it and figure out where you're going wrong. So the magnitude's realistic, yeah, seems to be. Okay. So what is the direction of the vector? Now that's going to be a little more challenging. Let's say we have a vector off in a direction. We want to figure out what its length is. We could figure out the length easy enough, but what's its direction? Well, if we put it on a coordinate system like this, and we could put it anywhere on the coordinate system, so the easiest is to put the origin of the vector at the origin itself. We now can look at the angle pointing off in this direction. We have rise over run. We can figure out the angle over here by doing the tangent is the opposite over the adjacent is equal to the tangent of this angle. So we can use arctangent to figure out the angle. So here's a couple of pointers. When the motion you're describing is confined to the surface of the Earth, it's convenient to have the x-axis as east, y-axis is north. That's just kind of a convention. It doesn't have to be that way, but that's what we tend to do. If the motion involves motion through the air, generally we're going to have the positive, or the x as the horizontal and the y as the vertical, and those will both be positive. If it's on a hill or on a ramp or on some kind of slanted thing, it's convenient to place the x-axis in the direction of motion, basically following the angle of the ramp, and then the y-axis perpendicular to the x-axis, or perpendicular to the ramp. And
defining a coordinate system allows you to describe a vector in a different way. Vector A, shown here for example, could be described as going 5 units in the positive x direction and 4 units in the positive y direction. You can represent this information in the form of 2 vectors and label them AX and AY. Notice that AX is parallel to the x-axis and AY is parallel to the y-axis. Now if you add AX and AY, the resultant is the original vector. You can therefore conclude that a vector can be broken into its components, which are a vector parallel to the x-axis and another parallel to the y-axis. This vector equation is always true. The process of breaking a vector into its components is sometimes called vector resolution. Notice that the original vector is the hypotenuse of a right triangle. This means that the magnitude of the original vector will always be larger than the magnitudes of either component vector. Another reason for choosing a coordinate system is that the direction of any vector can be specified relative to those coordinates. The direction of a vector is defined as the angle that the vector makes with the x-axis, measured counterclockwise. In the coordinate system here, the angle 0 tells the direction of the vector A. All algebraic calculations involve only the positive components of vectors, not the vectors themselves. In addition to measuring the lengths of the components' vectors graphically, you can find the components by using trigonometry. The components are calculated using these equations, where the angle 0 is measured counterclockwise from the positive x-axis. The sign of a component depends upon which of the 4 quadrants the component is in, as shown here. When the angle that the vector makes with the x-axis is larger than 90 degrees, the sign of one or more components is negative.
Okay. All right, and again, this is just a whole coordinate system, kind of a review of when the x is positive or negative. Now, Another thing you can do with these vectors is if you want to add more than one vector, you can do that. You just have to take each vector and break it down into its x and y components. So you'll take A and make that a x and a y, and then you'll take B and bx, by, C. Again, rise over run, you know, for each of the vectors. And then you could add up all of the x parts of it and get the rx. You could then add up all the y and get the ry, and then you could reconstruct the original vector. So ry then would be all of the y's, and you now have, if you know what rx and ry are, because it's a right angle, Pythagorean theorem, and you could figure out what the length of the resultant vector is for all of them. Again, you have to use the vector resolution to break it down, and then you put it back. Here again, we're going to use we're going to use trigonometry to figure out what the angle is. Since tangent is equal to opposite over adjacent, arctangent will give us the angle itself, the number for the angle itself. So again, you could use that arctangent key on your calculator, and just be aware of the fact that depending on what quadrant you're in as to whether you're going to have a positive or negative. You're going to use these techniques to resolve vectors, and resolving vectors